Okay, so this is, at least the main result is joint work with Jan Venden Heuvel. It would have been new at the original time of the conference. It's now been published at the beginning of this year. So I'm going to start out with a little bit of a prologue to try to show you that what I'm doing actually has some serious connections. So Nesatril and Sona de Mendes have a program to develop a theory of sparse graph classes. And they want a theory that preserves algorithmic and structural properties of simple sparse graphs when you pass on to more complicated sparse graphs. And it's been quite successful. To give their characterization, I need the notion of a T-shallow minor. So what's a T-shallow minor? It's just a regular minor, except that you can only contract parts that have small radius. So for a T-shallow minor, the parts you contract have to have radius at most T. Okay, and so what does it mean for a class to have bounded expansion? It means that there's a function or sequence of integers, so that for every natural number T, and for every graph in the class, and for every T shallow minor, so this T and this T, the edge density of the minor is at most C sub T. Okay, so that turns out to be a very useful definition. Maybe it's not apparent why, but and a more general definition has the same form, except with the thing that you're bounding is not the edge density of the minor, but the peak size. Clearly, everything that has bounded expansion is nowhere dense. A little bit of thought shows that this class of graphs is nowhere dense, but does not have bounded expansion. And some of the examples that have been of theorems that have been proved using these notions. So supposing C is a class with bounded expansion, then every property of graphs definable in first order logic can be decided in linear time on this class. And you have the same, you have a similar result for nowhere dense classes. The difference is that you have to give up a little bit on the linear time. And well, if you're not so happy with all this computer science and logic stuff, then maybe you like posets. So here's a theorem that G be a class with bounded expansion, H positive integer. Then there's a function C such that every poset whose cover graph is in the class satisfies the dimension of the poset is less than or equal to 4 to this C of the height. Okay, I'm not defining any of these notions, but if you know about posets, this makes some kind of sense to you. And even more strongly, you can use this idea to characterize what it means to have to be nowhere dense, at least for monotone classes of graphs. So if you have a monotone class of graphs, it's nowhere dense if and only if for every integer h, and every epsilon greater than 0, there exists a constant C such that every n element pulse at P whose cover graph is in G and whose height is at most H satisfies the dimension is less than or equal to C times n to the epsilon. Okay, so this is not just a result that's true for nowhere dense classes. It actually defines nowhere dense classes. So if you look at a monotone class of graphs, then it's nowhere dense if and only if this complicated statement about posets is true. So somehow the notion that Nesatro and Osona de Mendes came up with is very broad. Let me give one more example before I go on. The exact distance P graph of G is the graph that you get by using the vertices of G and putting an edge in between two vertices if the distance between them is exactly P. And then if a class has bounded expansion, then for every odd P, there exists a constant so that for every graph in the class, the chromatic number of the exact distance P graph is less than or equal to C. Okay, so this is a theorem that I'll come back to. Okay, so the prologue is over, and now I'm going to start doing some stuff that looks sort of off the wall and maybe just a curiosity. But okay, let me try it anyway. So I want to define the notion of R coloring number. So what's the situation? We have a graph, we have a total ordering on the vertices of the graph. Okay, and supposing we take two of these ordered vertices, then we're going to take a path from the bigger one to the smaller one. And I'm also going to use the notation that if I put the circle above a path, it means look at the inner vertices. The path you get by throwing away the ends. Oh, wrong way. Okay, so a path is, well, there are two notions here. Let's do the weak one first. It's weak if the smaller endpoint is less than all the vertices in the path. Okay, so an example of a weak path would be this blue thing. Okay, the path is strong. What does that mean? It means that we're going to strengthen the requirement. So the requirement is that the inner vertices of the path have to be bigger than the big thing. So this is an example of a strong path. Okay, so vertex U is then weakly reachable or strongly reachable. Well, how much reachable? It's this R reachable. So U is weakly R reachable from Y if there is a weak YU path of length R. Okay, so this is a very basic notion for us. Okay, and now what are the R coloring numbers? Well, Dietzel defines the coloring number of a graph to be the degeneracy of the graph plus 1. So in other words, what's the coloring number? You can order the vertices of the graph so that for any particular vertex, the number of neighbors that came before is at most the coloring. Well, no, size of V, the neighbors of V, L for left that came before, and I don't want open, I want closed neighborhood. So this, this measures how bad V is, counting V, all the things that come before. And if you can, if this number is bounded by, say, B for every vertex, then the coloring number of the graph is bounded by B. Okay, so now what I'm going to do here is I'm going to extend that definition, both the name and the concept, to our coloring numbers. Okay, and there's going to be a weak version and a strong version. Okay, and what's going on here? Well, this is a notion that's defined in terms of orderings. I mean, here I implicitly had an ordering. So supposing you have an ordering fixed, then the weak coloring number, the weak R coloring number of the graph with respect to this ordering is the worst case of a vertex in it. That means it's the max over all vertices of the size of the set of vertices that are reachable, weakly are reachable from V. And there's a similar definition for the strong version. Okay, and then what's the weak coloring number of G? Well, what you do is you find the best ordering, the one that makes this number be as small as possible. Okay, and this the strong version too. So I'm going to try to tell you why Cheng Yang and I defined this in 2003. But at the time, well, we had some reason for doing it, but not a very strong reason. But we could prove this theorem, that they were connected. So we can bound the strong coloring number is easily bounded in terms of the weak coloring number, but again, the weak coloring number is bounded in terms of the strong coloring number. Okay, but let's look at some applications to see that maybe, at least in the case of strong 2 coloring number, the concept is interesting. So what am I going to do? I'm going to take a graph, and I'm going to order the vertices. So this black line is not supposed to have anything to do with edges. It's just an ordering on the vertices. What ordering it is? Well, it's an ordering L that witnesses the 2 coloring number of the graph. Okay, so what does that mean? It means that whenever I'm looking at a vertex here, the number of things I can get to by going like this and back, or by going straight back, is at most this number. Okay, and now I want to use it to bound the list acyclic chromatic number of the graph. So what's an acyclic coloring? An acyclic coloring is a coloring that it was proper. And on top of being proper, it has to assign at least 3 colors to every cycle. So what I claim is, if you color this graph readily in this order, you get an acyclic coloring, even using the lists. And well, okay, I have to tell you what reading means. Reading means that when I assign a color to this vertex here, it should be different than the color of any previous vertex from which I can get to by a strong 2 path. Okay, and now why does that give me an acyclic coloring? Just look at a cycle. So look at any cycle. That cycle has a last vertex. Okay, now, of course, this cycle has to have, well, let's look at colors. This guy got colored, say, red. Now, the other neighbor of this last vertex on the cycle has to get a color. And because there's a strong 2 path from it to the red vertex, it can't be red. And then this last guy is adjacent to these guys with 2 different colors, so we're forced to use 3 colors. Okay. Let's try again. Well, okay. Why is that interesting? Well, it's interesting because it's interesting for classes of graphs where you can bound the 2 coloring number. Okay. So for example, for planar graphs, the 2 coloring number is 8. Okay, there are better bounds than 8 for this, but at least it shows what happens in general. Okay, so for any class with bounded 2 coloring number, you have a bound on the acyclic chromatic number. How about star chromatic number? Well, in fact, star list chromatic number. So in star coloring, what you're trying to do is you're trying to color properly so that any P4 gets 3 colors. So this time I want to take an ordering that witnesses the weak 2 coloring number. And I want to look at my P4. It has 2 vertices. Maybe I should have drawn it like this. I don't want to bias the ordering on it. But it has 2 vertices in the middle, 2 vertices of degree 2. And one of them is bigger than the other. So let's draw that here. Okay, so maybe this is the bigger guy. So what I want to now do is I want to look at this guy and this guy. So I see this one already. There it is. How about the other one? That guy, where is he? He might be here. He might be here. He might be here. The latter 2 don't make much difference. But whether or not this guy is bigger than this one, or whether he is smaller, does make a difference. So let's look at both cases. Well, as we've already seen in this case, we have to use 3 colors on those 3 vertices. On the other hand, if it's sitting out here, then we have that from this vertex, I can reach this vertex and then this vertex weakly. So here it's weakly, not strongly. Okay. Yeah. So when I color greedily in this way, I have to end up with a star color. And okay, so in her thesis, Al-Mohin showed that the weak coloring number of planar graphs is at most 23. It turns out that this bound for the list chromatic number of planar graph, list star chromatic number of planar graphs is best possible. Well, best known. Okay, the lower bound is 10. Yeah, actually the lower bound is 10 too, both for this number and for this number. We think strongly that we can prove less than or equal to 18, but we haven't done it yet. Okay. Okay, so now I want to talk, instead of easy little examples, I want to talk about the origins. Okay, so the origins come from a paper of Tao and Chen and Schelp. So they showed that Ramsey numbers are linear. So, well, under certain circumstances, okay? So Erdős conjectured, and eventually it was proved, that the class of K-degenerate graphs has linear Ramsey numbers. Okay, but it took a long time to prove that. In 1983, using the regularity lemma, these authors proved the case where the maximum degree is Dowda. The maximum degree is Dowda. Okay, bounding the strong two-coloring number comes in between. Okay, so planar graphs, for example, have bounded two-coloring number, but not bounded maximum degree. So I'd like to say something about the combinatorics of these two arguments. Of course, I'm not going to touch the regularity stuff. But the idea is that you have your graph G. Again, this is some ordering of the vertices. And you have a big graph that you're trying to find G in. So you take the first, the second, the third, etc., and you're making an embedding. Okay, so now we come to a new vertex we're going to try to embed. Where can we embed it? Well, we have to respect edges that go back. So when we choose this, we have to choose it inside the neighborhood of this vertex. Okay. But by the properties of regularity, we know that we'll always, almost, in fact, yeah, we know that all the, without using any properties, I'm sorry, we know that all these possible vertices work. But there's a danger when we pick one. When we pick one of these vertices, we may harm one of these other sets that is waiting to be used. Because this guy could be adjacent to this one, and he could be adjacent to this one, and he could be adjacent to this one. So when that happens, you see, when we pick this guy, we're going to have to cut down this set. We're going to have to cut down this set, and we're going to have to cut down this set. But using the magic of regularity, almost all elements, maybe there are a few exceptional elements that don't work, but almost all elements work for this set. And almost all elements work for this set. So these are the bad ones that don't work. And almost all elements work for this set. And we can continue the process. But in the original argument, that works because Dowda is bounded, so there are not very many of these guys. What Chen and Schelp did was they recognized that it's okay to have lots of neighbors out here, as long as their neighborhoods look very much the same. So if instead of having 3 different sets here as the target, if they were all the same, then it doesn't matter how many times we repeat it. Doesn't matter, I mean, however many we have out here, as long as they're all the same, is still only a few bad guys. Okay, and now this is where true reachability comes in, because what determines this set? its neighbors back here. Okay, but okay, it's neighbors that have already been embedded. But this guy that's causing trouble is too reachable from the vertex we're dealing with. So there are only a bounded number of these guys. And since there are only a bounded number of these guys, there's only a bounded number of subsets up here that can be defined. And the argument goes through. Okay, that's very fast, but that's the idea. Okay, and I was amazed by it when I saw it, and Trotter too. And we had to use it, and we made use of it for coloring, for game coloring in planar graphs. I won't go into that because I want to de-emphasize game coloring here. But yeah, the idea was very nice. Yeah, maybe one more example. So, of course, the dates are way after 2003, but with Van der Hoeven and one of his students, Kierstead, we provided numbers for the Nesertil-Osona-Dominguez proof. Okay, for exact distance. In the case where the planar graph, we were looking at planar graphs, and when the p was 3. So their argument provided that nice number as a bound for the chromatic number. We were able to get it down to 105, essentially using this argument. Took a little bit of modification at the end. So yeah, so, but anyway, for any graph G, the chromatic number of its distance P graph, or P odd, is bounded by not its weak 2 coloring number, not its weak P coloring number, but its weak 2P minus 1 coloring number. So, and yeah, my student knocked that back down to this, to 95. Okay, so more examples. Right, so here's the real idea that I want to push now, and that's that you can use the game coloring numbers, not the ordinary coloring numbers to play games. So here's a game. I want to play a game between 2 players, Alice and Bob. Bob's going to decide who goes first. You can pick Alice to go first, or he can go first himself. And then they take turns picking vertices. So Alice is red and Bob is blue. So they're picking these vertices. Okay, and what's the score of the game? Well, you just look at the, strong coloring number, the strong R coloring number of the order that you created with this game, and that's the score. Alice's job is to try to make the score as small as possible. And Bob's job is to, well, try to drive it up. But that's misleading, because actually when we apply this technique, Alice is doing her job. Bob is just ignoring his job. And maybe things go bad, maybe they don't. Okay. So Alice tries for a minimum score, Bob tries for a maximum score, and the game coloring number is the S that Alice has a strategy to achieve. Okay, and we bounded these game coloring numbers using weak coloring numbers. In fact, that's why we invented weak coloring numbers. And that you gave us a bound using the strong coloring number. At the time, well, we put it in a small journal because we didn't see any real reason for proving this general statement. We only knew uses for the case when R was 1 or one special case when R was 2, but we could prove the whole thing, so we wrote it down. So here's an example using the game coloring number, the one game coloring number. So 2 graphs pack if you can embed them both in, well, if you can embed one into the complement of the other. And Sauer and Spencer, fairly well-known theorem is that if the maximum degrees of the graph, the product of the maximum degrees times 2 is less than the number of vertices, then the 2 graphs pack. With Kostochka, I proved that you can get rid of, on each side, you can get rid of one of those maximum degrees and replace it by game coloring number. Or if you don't like game coloring number, you can replace it by strong 2 coloring number. Okay, and for instance, for planar graphs, these are constants. So you go from a quadratic bound to a linear bound. So let's see how that goes. So we don't have this ordering yet. We're creating an ordering on the graph. Okay, and as we go, we group vertices from G1 with vertices from G2. Okay, and what's the goal of this process? The goal of the process is to keep all the degrees, all the left degrees small, here too. We would like these degrees small, these degrees small. And we want to have the property that inside here, we can embed this part into the complement of this part. So that's the invariant we want to maintain. We don't care about whether we change the embedding as we go, that's legal. But we have to keep extending what we have. So the next time we have to get something that looks like this. So how are we going to do that? Well, we're going to play 2 games. There's going to be Alice and Bob playing on G1. And there's going I really wanted to make this a blue one. And there's going to be Alicia and Beto playing on G2. Okay, and okay, forgive me for sticking gender roles on, but Bob is in charge of the construction. And he's married to Alice, who's in charge of keeping family harmony. So what does family harmony mean? It means that these back degree conditions are met. Keep this small. And what does construction mean? It means that if this vertex has been picked, then Beto has to pick a vertex so that you can extend the picture. So that's the construction part. And so what happens, say Alice just played here and Beto just played here. Okay, so Beto played, you know, construction is, creates chaos. So the opposite of harmony. Alicia has to fix that chaos. So what she's really done is she's posed a challenge to Bob over here, who has to meet the challenge. So now we have this played, we have this played, we have the bigger picture. And now on the other side, you see Bob created chaos. Alicia has to recreate harmony. And down here, Beto has to do the construction. Okay, and this whole process works now, provided that, well, Alice has to have a strategy. That's the game coloring part. Alicia has to have a strategy, the game coloring part. And Bob and Beto have to have strategies, but that comes directly from this proof. Okay, so I think this is the first real version of using game coloring for a really non-game problem. So now what ties everything I've been talking about together is this proof theorem of Zhu, that a graph has bounded expansion if and only if the sequence of strong coloring numbers are bounded. And of course, if the strong coloring numbers are bounded, then the weak coloring numbers are bounded and the game coloring numbers are bounded. So you can use any one of those ideas. Yeah, so the difference here is you could use game. And I'm running a little short on time, but let me just say that there's a similar idea that works for nowhere depths. Okay, so now this is okay. So this is the result I want to talk about. So you can ask the question: supposing you have a graph that has lots of different coloring numbers. The one strong coloring number, the two strong coloring number, the three strong coloring number. And according to the definition, for each one of those things, there's an ordering L that witnesses it. So is it true that there's one L that witnesses all the coloring numbers? Well, yeah. Is there one L that witnesses all the coloring numbers? And the answer is no. This is an example. So let's see what's going on here. Start with Kn. For every edge, I'm doing two things at once, sort of. So one thing is I'm going to subdivide this edge. And I'm also going to blow up the two ends. So I get a picture that looks like this. Okay, and I'm doing that for every edge. So if you do this, you can calculate that the strong one coloring number of the graph is 2t plus, oh, yeah, I should have said, okay, so I picked, the blow up is the t, it's smaller than the n by a lot. N is the size of the picture. Okay, so this is just the minimum degree of the graph. You can put all the x vertices at the end, and all the z vertices at the beginning. And when you do that, well, these have degree bounded by that. And these guys form an independent set at the beginning. So, and let me just point out that it's a bad idea from the point of view of the one coloring number to have a z vertex that has lots of x vertices before, that has lots of its neighborhood before. Now, how about the two coloring, the strong two coloring number here? For this, instead of putting all these guys at the end, well, that would be it. Put them all at the end, then if you took the last z, it would be adjacent to all the z's, and that would be huge. Okay. Not much time to analyze everything, but yeah, so this example of a graph has relatively small one coloring number, strong one coloring number, relatively strong, relatively small, strong two coloring number. But any one order you pick is going to drive things up. All right, so we have a no here. So Jorak asked the real question. So what did he ask? He wants a function from natural numbers to natural numbers. And so for every such function, there should be another function. So that for every graph in a class, well, this is the class that has bounded strong coloring number, and the bounds are given by this C. You want an ordering L star that bounds all these numbers at the same time. So given this function, that's essentially giving the class, okay, for the class. But for any class that looks like this, there should be a new function, a bigger function C star, so that for all graphs in the class, there's an ordering that witnesses this bound for their strong R coloring numbers. So one possibility would have been that C star might have been C, but we just showed that didn't work. So our theorem, so this is with Bend and Hoivoy, is that the question has a yes answer. And we get explicit bounds. Let's see, where are they here? So the lower bound comes from being more careful with the construction. Can everybody hear me? No, okay, good. Okay, the upper bound is what I want to talk about now. Yeah, okay, here's another application of the golden ratio. These bounds are very far apart. This one, I don't believe at all, because it's only based on looking at two values of C. I'm rushing myself too much. So let's talk about the inspiration for the upper bound. Okay, again, I'm only going to look at two values. So supposing we have an R and R prime given to us. And what we're trying to do is we're trying to find one ordering that works for both of them. in the sense that there's an upper bound. And so what we're going to prove is that we can bound the strong R coloring number of the graph in terms of the game coloring number, which of course we know we can bound in. Well, okay, so I mean, there is a bound here, and we're allowed to use something more as long as we specify what the something more is. This is what it is. And our argument is going to be based on the game coloring number. So how does this go? We want to, well, we're going to have two players. There's going to be Alice, and there's going to be Alicia. And Alice thinks she's playing the R game, and Alicia thinks she's playing the R prime game. But they're playing on the same set of vertices, so it all makes sense. So, you know, these vertices start to be played. Let's say Alice goes first. Well, Alicia has a strategy for her game, so she knows how to move so that harmony is preserved in her game. And so Alice thinks of this move by Alicia as really a move by Bob that she has to fix. So she fixes it. And Alicia does the same thing. She fixes Alice's move, treating it as a move by Beto. And that process continues, and we get the bounds we want. Okay, so that works for two. But it doesn't work for more than two because all this game theory only works all this game theory only works for two players. Maybe I'm worried that I skipped some stuff as I went, and I should have mentioned that one of the uses of the weak coloring number, I guess I did say this, is that it bounds the game coloring number. So for more than two arguments, we have to use another strategy. So it's not really a game proof anymore, but what's going on in the general argument is that you have infinitely many players, but the government is going to set some rules for how they interact with each other. So they have to behave socially, properly. So for instance, they have to wear masks in public, and more dangerous ones have to wear more powerful masks. Think of it that way. Yeah, and actually the strategy comes from an old paper with Yang. Again, it was a paper that we thought was just a curiosity. It wasn't even about game coloring. It was about game chromatic number, where Alice got to make many moves and Bob only got to make one move. So it was a very special situation. But Ching found this strategy, and it was just what Jan and I needed for the proof that we're doing here. So I guess my time's up right now, and I'll say thank you for listening. And yeah, I get my main point here is that game coloring number is useful.